Good afternoon. I'm Jay Scott, editor of High Performing Buildings magazine. Thank you for joining us for today's webinar, part of the HPB Supplier Webinar Series. The series provides information to HPB readers and others about technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. Baltimore Air Coil Company would like to welcome you to this webinar titled Closed Loop Systems, Open Tower Heat Exchanger, or Fluid Cooler, which is best for your application. Today's presenters are Andrew Rushworth and Frank Morrison. Andrew joined the BAC Global Marketing team this March as Product Platform Manager for Closed Circuit Cooling Towers. Andrew has spent his career in marketing, initially working for leading food and beverage manufacturers in Europe before moving into global B2B marketing with the S.C. Johnson Group of companies. His experience includes new product development, marketing strategy, product positioning, and value proposition development. Andrew has his bachelor's degree from the University of London and an MA in Management Systems and Sciences from the University of Hull in England. Frank is currently Technical Director, Global Marketing at Baltimore Air Coil Company. Frank has worked in both product engineering and research and development at BAC, as well as managed the R&D labs and the Design Operations Group before moving to marketing, where he was Closed Circuit Product Manager. He earned a BSME from Drexel University and an MBA from Loyola College. Frank is active in industry organizations such as ASHRAE, AHRI, and the Cooling Technology Institute. He is an inventor or co-inventor on 10 U.S. patents and has authored numerous ASHRAE journal articles and technical papers. And now we turn the webinar over to Andrew. Thank you.
Okay, thank you for the introductions, Jay. Hello, everybody, and welcome to today's webinar. As Jay mentioned, Frank and I are going to talk to you about closed-loop heat rejection systems with the aim of shedding a little more light on all the aspects that you might need to consider when making the best choice for your next project. Our approach to walking you through this field is laid out here in the agenda. We're going to start by reviewing both open and closed-loop heating systems, pulling apart the differences and relative merits of both, look at ways to close the loop, and then compare two of those ways from three different directions: the operational perspective, the energy each might consume, and first cost versus installed costs. We will summarize our findings and then throw it open to questions at the end. If I could ask you to type in your questions as we go along, we'll group them and look to answer at least one question from each of the groups. However, we won't be able to answer all of the questions, no doubt, during this webinar, but we will try to answer all of them via email over the next few days. So, without further ado, let me hand you over to Frank.
Thank you, Andrew, and welcome everyone to our webinar. Let's first talk about open-loop cooling systems. And of course, what we're talking about there are open circuit cooling towers. They come in a variety of sizes and shapes and designs. And what we start off with here is an induced draft counterflow unit. What you see here at the bottom is the water which goes out to the load to be cooled, returns warm or hot, and is sprayed over what is called a fill deck or heat transfer surface. Air is induced up through the cooling tower where the water and air mix and the water is cooled before returning back to the system load. The next type of cooling tower is an induced draft crossflow. This is a little different design. Basically, we're taking the hot water and putting it in each side of the tower where it falls over the fill pack by gravity. Air is again induced up through the cooling tower with the fan you see in the center of the unit, and the water is cooled and is collected in the water basin and then goes back out to the load. there is another type of cooling tower known as a forced draft counterflow cooling tower. Okay. Sorry, we have a little delay in our slide movement. A forced draft counterflow cooling tower, which in this instance has a centrifugal fan. The air is blown up through the fill pack, and the hot water is sprayed down over the fill, where again the air and water mix to be cooled. This type of cooling tower is often used for indoor applications in cold weather areas or in high security installations, or for sound sensitive sites. Now, open circuit cooling towers are highly efficient, and that is due to the direct contact between the water and air on the fill surface. There's also a large amount of heat transfer surface area in these units, which enhances the efficiency. The heat transfer is also based on evaporative heat transfer, because to evaporate 1 pound of water requires 1,000 BTUs, so it takes away a lot of heat with just a small amount of water. So you lose about 2% of the water to evaporation, but that evaporation then cools the remainder of the water very efficiently close to the wet bulb of the air. And that's the last point, where the cooling tower takes advantage of what is called the wet bulb depression of the air. In Baltimore, on a 95-degree day, you can have a 78-degree wet bulb. Thus, you can cool the water down below the dry bulb of the air and get very efficient temperatures back to your cooling load. Now, here's a typical open-loop cooling system, which is based on a water-cooled chiller with an open-circuit cooling tower. You see in the center there is the chiller and the chilled water circuit that is removing heat from the building, the heat load from the building. Now, that chilled water circuit is a closed loop. On the other hand, on the other side, where the condenser of the chiller is, we have an open loop. The water from the cooling tower is pumped through the chiller condenser. It picks up heat and returns to the cooling tower to be cooled. Now, the tower side of the heat exchanger is open to the atmosphere. This means that system components can be exposed to airborne contaminants. Now, these contaminants can include dust, dirt, pollen, boiler exhaust, and the like. So to maintain peak efficiency, you must keep the system clean. And that can be done through a proper water treatment program. For certain applications, you may want to consider the use of side stream filtration. Say your cooling tower is located near a stand of trees that could have pollen in the springtime, that could provide a load of debris that could enter the tower. So by having side stream filtration, you keep the solid content of the water down, but that also makes your water treatment program much more effective. Now, heat exchangers will require periodic cleaning. You can see here the difference between a clean plate and frame heat exchanger plate and one that's been fouled, as well as a shell and tube heat exchanger that is fouled. So you need to make sure these are cleaned when you see the performance starting to degrade in the heat exchangers. So be sure to follow instructions in the manufacturer's operation and maintenance manuals for all your equipment in the system. Now, many traditional open cooling systems can benefit by closing the loop. This helps you to maintain high performance over time, reducing energy consumption. It also reduces the need for periodic cleaning. Now, you can consider the chiller fouling factors from AHRI standard 550, 590. The standard fouling factor for the rating on the condenser side is 0.025. Yet on the closed evaporator side, which is the chilled water side, it is 00001. This makes about a 1.2% difference in energy efficiency, but if you would close the condenser side, you would save energy, and it would be an initial and ongoing energy savings over time. Now, these are just the fouling factors as it comes from the factory in the rating. In the real world, the fouling can be much more severe, all the way up to 0.04 or greater, and that can have as much as a 44% increase in power required to do the same cooling duty. So keep that in mind. With a closed loop, you have location flexibility. The heat rejection equipment can actually be located at grade or even below the load. You can reduce installation costs and enhance accessibility for maintenance. Another advantage is that the architects can help to, use that ability to locate the location flexibility to help protect the aesthetics of the building in certain instances. You can often reduce the pumping power required thanks to the closed loop cooling. There's no need to deal with the lift required to the top of cooling towers on the open loop to overcome. Now, many cooling systems require a closed loop for reliable long-term operation. Often, heat exchangers and distributed systems have small passages. This includes tube-and-tube coaxial condensers, brazed plate heat exchangers, and these heat exchangers are difficult or impossible to clean once fouled. Examples of such equipment include water source heat pumps, water-cooled variable refrigerant flow systems, modular chillers, and industrial equipment such as air compressors and welding machines. Here is a sample diagram of a water source heat pump loop. You can see this one is based on a closed circuit cooling tower with a boiler, and all the orange boxes there are your water source heat pumps located throughout the building, but each one of those has either a brazed plate or a coaxial heat exchanger in them that can be fouled or clogged if this was an open loop. So that's why closed loops are used in these instances. So how can you close the loop? You could use a dry cooler, but you pay an energy penalty on the system through higher design fluid temperatures. If you remember the Baltimore design day that I mentioned earlier with the 95-degree dry bulb, you would be lucky to get 105 or 110 degrees off the dry cooler during that design day, which would then be an energy penalty on the system. And remember now, the heat rejection is often the lowest energy part of the system. On a typical chiller system, water-cooled chiller, you're operating around 0.06 kW per ton. The heat rejection operates at 0.06 kW per ton, or 90% less. So you want to protect and have the energy reduction on the higher energy part of the system, which would be, in that case, the chiller. It also requires more fan energy to do the cooling in a dry mode. You have to move a lot of air there compared to the evaporative cooling process. Now, you can use an adiabatic fluid cooler, which has lower energy use than a dry cooler, as the entering air is pre-cooled before entering the dry heat exchanger. And you can see a photo of one there in the middle with the blue cooling pads. Water is dribbled over these pads, air goes over the wetted pad, and is cooled adiabatically close to the wet bulb of the air. Now that enhances the dry performance of the coil behind it. Now this does add cost over the dry cooler option. You can also use a ground source heat exchanger, which can be very energy efficient but costly. And you also need space for the well field. You see a diagram of that on the right-hand side of the screen at the bottom. And what I found from my experience and research has been that hybrid ground source systems, which combine a well field plus a closed-circuit cooling tower or plate and frame heat exchanger and cooling tower can actually lower your first cost while you're achieving the same or better energy efficiency and at lower risk. At minimum, I recommend that consulting engineers consider putting in connections so that should the well field heat up beyond what can cool the building, or that perhaps some of the wells are not properly grouted, you can then put in a rescue fluid cooler and connect it easily into the system in the future. So that little bit of extra piping can provide an insurance policy in the future. So let's look at energy efficient evaporative heat rejection, which gives us two choices for system designers: an open circuit cooling tower coupled with a heat exchanger, or a closed circuit cooling tower, which is also known as a fluid cooler. You see a photo of a plate and frame there on the left. In the center, you see a diagram of the plate and frame pulled apart with the alternating hot and cold fluid paths through the plates of the heat exchanger. And on the right-hand side, you see a fluid cooler. Now keep in mind that both of these heat rejection systems are capable of returning the same fluid temperature to the system they are connected to. So the energy efficiency of the bigger system will be the same. Now let me just say that when you're comparing these systems, or when you're comparing any heat rejection alternative, remember that you need to level the playing field. Both open and closed circuit cooling towers are certified per CTI standard 201RS. This is also referred to as ECC certification in Europe, which is Eurovent Certita, which is a partnership between Eurovent and CTI, in case you're designing any projects in Europe. Now, plate and frame heat exchangers are certified per AHRI 400. There are many participating manufacturers in both of these programs, and by using certified equipment, that allows for fair comparisons and also helps to assure that design efficiency is achieved once your installation is up and operating. You can check major manufacturers' websites for wording for your project specs. Now, closing a chiller loop, we're going to first do it with a cooling tower and heat exchanger. We see on the chiller there is in the middle, and you have the closed loop on the heat load side of the building, the chilled water loop. And then we place a plate and frame heat exchanger and pump the fluid, hot fluid from the refrigerant condenser through the closed loop side of the heat exchanger. Now, on the other side of the heat exchanger plates, we're pumping the cooling tower fluid through an open loop to the cooling tower. Now, on a cooling tower heat exchanger system, the process fluid is contained in a clean closed loop on one side of the plates. The other side, of course, is open. The plate and frame heat exchangers typically have high overall U values, which is the overall heat transfer coefficient. The pressure drops are generally reasonable, usually 10 psi or less on each side. However, these high U values are often susceptible to fouling due to the high U values. So just a little bit of fouling can seriously decrease that high overall heat transfer coefficient. These plates are also very tightly packed, about 1/8 inch apart, so they are susceptible to clogging. So you need to make sure that you have proper strainers in front of the heat exchanger to avoid that. You can see a photo there of a inlet to a plate and frame heat exchanger pack that became clogged with dirt and debris. Now, the plate and frame heat exchanger can be cleaned You need to allow adequate room in the equipment room for this cleaning. We also suggest you have a drain available nearby, because when you take the plate pack apart, you're going to get some water out of it, and you're going to be cleaning the plates. You also should have new gaskets available should you need them when you're putting the plate pack back together. And you should follow proper plate pack tightening procedures. If you over-tighten, you can have pressure drop issues as well as performance issues, because you need to maintain the proper spacing between each plate. Now, the heat exchanger is typically located in the equipment room, which means that the equipment room needs to be larger, which reduces the rentable area in the building. So that should be taken into account. Because the heat exchanger is in the equipment room, however, you do not need glycol for freeze protection, although you should follow the proper cold weather operation procedures for cooling the open circuit cooling tower when you're operating during the winter months. And here's an important point, in that the cooling tower selection is different than the traditional open loop system. In a traditional open loop system, you're designing for 95-degree hot water, say 85-degree off the cooling tower at, say, a 78-degree wet bulb with no heat exchanger in the system. To get 85-degree water back to the tower with a 3-degree approach across the heat exchanger, you'd have to cool you'd have to have conditions of 92-degree hot water, 82-degree leaving water off the tower at the 78-degree wet bulb. So you basically have a closer approach on the cooling tower. You go from 7 degrees, which is the leaving fluid temperature minus the wet bulb, to an approach of 4 degrees, which is 82 degrees to 78. So the tower does grow in size in these cases. Now let's look at closing a chiller loop with a fluid cooler. Here we have the same closed loop chilled water system on the evaporator side of the chiller, but on the condenser side we have the closed loop, where the warm water from the condenser is pumped to a coil that is located in the closed circuit cooling tower, and water is sprayed from the sump of the unit up over the coil. Air is induced into the unit, and the evaporative heat transfer occurs on the surface of the coil, cooling the fluid within the coil. That water or glycol returns from the coil of the closed circuit tower back to the condenser to pick up more heat from the condenser. But in this case, both sides are closed, both the chill water side and the condenser side. Now let's look at various types of closed circuit cooling towers. Here is shown an induced draft counterflow tower, where the hot fluid enters the top of the coil, traverses through a serpentine tube bundle, and leaves cooled out of the bottom. The water in the sump, which is shown in blue, is pumped up over the coil. Air is induced through the fan at the top of the unit, and the evaporative heat transfer occurs inside in that tube bundle array, where it basically cools what's inside the tube. And what we see on the left-hand side of the screen is a typical coil or tube bundle that is installed in the closed circuit cooling tower. Another type of closed circuit cooling tower is a forced draft counterflow, and this particular one is based on a centrifugal fan unit, which again can be good for indoor applications that can handle external static pressure, but it basically works on the same principle, except the air is forced up through the tube bundle with the fan at the bottom. Another type of cooling tower that's been introduced in the past few years is known as induced draft combined flow designs. This is where the coil, which you see is located at the top of the unit, has water sprayed over it, and air also is brought down over the coil surface. The spray water picks up heat and then falls off the bottom of the coil onto a fill deck, which is the same as what could be used in an open circuit cooling tower. And that water is then subcooled below the temperature that can be achievable without the fill deck. And that allows you to, number one, reduce the amount of coil you need, which lowers the weight of the unit, but it also can improve the heat transfer ability of the coil itself such that it's greater than what a traditional coil-only design would be. And you can achieve closer approaches at lower fan horsepowers. So this design has real advantages, and the last one being that the heat transfer in the coil area is actually primarily sensible heat transfer, not evaporative heat transfer. So, however, the evaporative heat transfer occurs primarily, about 70 to 80% of it, in the fill surface, which means that the coil surface stays much cleaner and does not scale. The scaling would then occur in the fill area where it can be easily removed and through the water treatment program. Now, a fluid cooler combines the function of a heat exchanger and cooling tower in one compact unit. This keeps the process fluid in a clean, closed loop, and it also saves space in the equipment room by taking the heat exchanger and putting it outside with the cooling tower. Pressure drops are usually less than 10 psi on the cooling loop, which is the same as a plate and frame. It is more resistant to fouling. There's no need to clean heat exchanger plates, as the fouling and any scaling can be controlled through the water treatment program. The external surface of the coil is very open, and the water can get in there, and the water treatment chemicals can get in there and take care of any fouling or scaling on the surface and keep them performing at peak efficiency. Another consideration is that because the spray water stays within the unit and doesn't have to be piped to an external heat exchanger, the open loop water volume is usually less in a fluid cooler than it is in an open tower. And as water treatment costs are proportional to the system volume, that would imply that the fluid cooler is less costly to treat. Now, the spray pump that recirculates the water from the cold water basin up to the spray system of the tower uses less energy than the typical cooling tower heat exchanger cold side pump. It is also easier to implement free cooling for economization in a fluid cooler system because of the less need for piping complexity. And you can often operate the fluid cooler dry in colder weather and or periods of low load. This allows you to either save water or minimize icing issues during very cold weather operation. Now, one thing also to consider is that the fluid cooler is heavier than an open circuit cooling tower, so additional steel grillage is required to support the fluid cooler. So we also did an installed case study, and for that I'm going to turn that back over to Andrew to tell you about that study.
Okay, thank you very much, Frank. That was very helpful. So, now we understand the framework for making a decision between different cooling tower options. Let's go to the next stage and understand what you might want to consider when making a choice between two different types of closed-circuit cooling towers. BAC commissioned a study from KJWW, now IMEG, an independent consulting engineering firm, to compare the installed cost and energy consumption of these systems under different conditions. The objective here was to identify and understand the differences between the systems to guide system designers and operators, enabling them to make the best heat rejection choice for future projects. IMEG looked at two closed-loop HVAC systems for us, a water-cooled chiller and a water source heat pump using two alternatives: a cooling tower coupled with a plate and frame heat exchanger and a fluid cooler. Both options were evaluated in differing building types with different heat loads across two ASHRAE climate zones using the major cities of Chicago and Dallas, which exhibit markedly different climates. Okay, so IMEG created designs for both the chiller and the water source heat pump systems in Chicago and Dallas. Firstly for an open tower and heat exchanger, and then repeated the exercise using a fluid cooler, identifying in great detail all the necessary elements to allow for an exhaustive comparison rather than just a general approximation of the requirements of each system as can be seen here in these schematics. Now, you can't see the specifics, but it's apparent that the designs are built as if for a real job. So every element has been taken into consideration here, and these are as accurate as we can get with regard to how a system might be built to meet the requirements as detailed on the slide. So if you look at how these elements can be broken out, the model includes equipment, and within equipment you're looking at towers, heat exchangers, pumps, water treatment, that kind of thing. For plumbing, we're including pipes, valves, strainers, anything else like that. The electrical group breaks down into wiring, conduits, breakers, disconnects, variable speed drives. There is a structural element, which is the steel support required to site the tower, and that's assuming that the job is new and not a replacement. Pressure gauges and flow meters as part of the necessary measurement and instrumentation. And then finally, evaluation was put on the real estate used within the building. RS means was used as the basis for the costs for the constituent elements, along with supplier quotes. IMEG also applied the appropriate cost multipliers for materials and labor in the respective cities. However, any cost approximation can only ever be a snapshot in time and based on the individual system design. So you have to take that into account. This is a case-by-case sort of environment. So the first aspect that was looked at was the comparative energy usage across two buildings with equivalent load requirements in Chicago, one using a chiller system and one using a water source heat pump. Generally, the connected horsepower usage was similar. In the two examples cited here, it was a match in the condo, and the fluid cooler used a little less in the hotel environment. But as I mentioned earlier, it must be remembered that each examination is a unique case dependent on the specific model applied, the exact layout, and a host of other variables, and each project must be individually evaluated. So I'm going to hand back over to Frank.
Okay, thank you, Andrew. Now we're going to look at the total installed cost overview for the two types of systems that were studied. The first being the water-cooled chiller option. And what we have here are graphs of total installed cost, and this is just total installed cost for the heat rejection portion of the system. And the y-axis is the cost in thousands of dollars. The fluid cooler is shown in green, and the blue bar is the cost for the open tower heat exchanger. So, for the 250-ton case, the fluid cooler was less costly on an installed basis in both Chicago and Dallas. For the 400-ton hotel case in Chicago, the fluid cooler was a little more costly than the tower heat exchanger. However, in Dallas, it was less costly. The 750-ton hospital case, you can see that the fluid cooler was quite a bit more expensive than the tower heat exchanger option. And in Dallas, the fluid cooler was again lower cost. We went back and looked at the numbers for Chicago, and what we found is that the cost of the glycol in the system along with the slightly larger fluid cooler that's required when you're cooling glycol, because it's not quite as efficient as water. That created an extra cost burden for the colder weather climates. So let's look at a deep dive on the 250-ton Chicago case for cooling an office building. We have on the right-hand side of the screen the fluid cooler, and on the left the open tower heat exchanger. And the first thing you really notice is that the equipment cost for the fluid cooler is $47,000 higher than the cost of the open tower heat exchanger equipment. And that's on, including freight and everything like that. And a lot of times folks will just look at that equipment cost and not go any further. So in this study, we wanted to look at what is the impact on the installed cost. So when you add all those up, we find that there's $65,000 less plumbing and piping required for the fluid cooler version, $8,000 less in the measuring equipment, the flow meters, pressure gauges, temperature sensors, $4,000 less wiring costs for the fluid cooler system, $6,000 less real estate because we don't take up space in the equipment room. The equipment room can shrink in size. And the additional structure required for the fluid cooler does add back in $4,000. And that's a total then installed cost savings for the fluid cooler system of $30,000 in this case, or 5% of the installed cost of the heat rejection system. Now this was based on a 50% ethylene glycol solution, which was chosen by our consulting engineers, IMEG, for this application. So looking at the insights that we've learned, in general, the fluid cooler and cooling tower heat exchanger had similar first costs. There were some factors that would throw the numbers one way or the other, but they were very similar. For the 250-ton case, the fluid cooler had the lowest installed cost versus cooling tower and heat exchanger. For the 400-ton and 750-ton cases, the fluid cooler was lower cost in Dallas, which is a water-only based system. In Chicago, the cooling tower and heat exchanger option were lower cost. The increased size of the fluid cooler due to the 50% ethylene glycol, along with the cost of the glycol in the system, impacted the overall cost of the system in this case. Now let's look at a system that needs a closed loop, which is a water source heat pump. Again, the y-axis is the installed cost for the system. The fluid cooler, again, is shown in green, and the blue is the open tower heat exchanger. For the 250-ton condo case, the fluid cooler offered lower installed costs in both Chicago and Dallas. For the 400-ton case, the costs were closer together, but still the fluid cooler was slightly better in both Chicago and Dallas. So again, let's do another deep dive, this time on the 400-ton condo in Chicago, which used 33% ethylene glycol in the cooling loop. For the fluid cooler, which is shown on the right, at $466,000 total installed cost. The cooling tower heat exchanger, shown on the left, at a cost of $484,000. But again, you notice that the equipment costs, which is just the heat exchangers and either cooling tower or fluid cooler, showed an increase of $53,000 for the fluid cooler. But this is more than offset by the $67,000 less in plumbing and piping, $8,500 less in measurement equipment required. Electrical did go up $6,000 for the fluid cooler option, but you offset that with the lower real estate costs by reclaiming part of your building for rentable space, and $4,500 for the additional structure required to support the fluid cooler. The total installed cost savings came out to $18,000 or 4% of the total installed cost. So let's look at what we can learn from this part of the study. Typically, water source heat pump systems utilize only closed-loop heat rejection systems. My experience has been that those who use open circuits on these type of systems are usually replacing heat pumps within a year. So keep that in mind. It's not a place to value engineer. For the 250-ton cases, it was evident that the fluid cooler had the lowest installed cost versus cooling tower and heat exchanger. The fluid cooler was as much as 8% lower cost versus the cooling tower heat exchanger option. On the 400-ton cases, the fluid cooler options were slightly more attractive than the cooling tower and heat exchanger. The fluid cooler was about 2% lower on average versus the cooling tower heat exchanger combination. So with the larger system, the difference narrowed, but it was still an advantage for the fluid cooler. So I'd like to now turn the mic back over to Andrew, who's going to review and sum up our webinar.
Okay, thank you very much, Frank. So at the beginning, we said we would look at the different evaporative systems, open and closed loop. We examined two ways to close the loop, these being open tower with heat exchanger and fluid cooler, and then compared these two in separate examples, looking at energy usage, operational aspects, and then a thorough review of the equipment costs and the total install costs. So what is the summary of all this learning? Closed-loop systems offer many advantages in terms of reliability, reduction in maintenance, and maintaining high performance levels over time compared to traditional open-loop systems. When only looking at the equipment purchase cost, fluid coolers are generally more expensive than the cooling tower and heat exchanger combinations. The total install cost of a fluid cooler can be lower than a cooling tower and heat exchanger due to the costs associated with plumbing, real estate, electrical, and other costs that we spoke about earlier. So when making a recommendation to an owner, the fully installed cost should be considered. In colder climates, the cost of glycol and the need for positive closure damper hoods to reduce heat loss on the water source heat pump systems must be taken into account. Fluid coolers, which combine the function of a cooling tower and heat exchanger into a single compact unit, are easier to incorporate into the system design with less risk than having to design, lay out, and pipe an open circuit cooling tower, pump, and heat exchanger combination. Fluid coolers offer the same or lower total connected energy as compared to cooling towers and heat exchanger combinations in closed-loop applications. And the ability of fluid coolers to operate dry in cooler weather can be an advantage in terms of water savings and cold weather operation. So, having concluded or made those summary statements, what is the overall conclusion here? What's the bottom line? So, use energy-efficient evaporative heat rejection when it's appropriate. Consider the overall benefits of closed-loop systems versus open systems, when that might be the higher or greater reliability, higher energy efficiency over time, and lower maintenance. And there are multiple ways you can achieve closing the loop. For each option, make sure that you evaluate the total energy use, the design complexity, the total install costs, not just the equipment costs, and then the impact of the climate zone you're intending to put the unit into. So that is the end of our presentation. It's now time for question and answers. We have a large group of questions from many of the different attendees. As I said earlier, we're going to pick questions from different groups and hopefully we'll be able to answer a sufficient number. So, Frank, I'm going to throw it over to you for the first question.
All right. Thank you, Andrew. We have quite an array of questions. which we really appreciate. And as Andrew mentioned earlier in the webinar, we're not going to be able to get to them all today, but we're going to try to answer as many as we can as possible. So the first question involves, do you have any backup for the claim that the hybrid geothermal heat pump loop is can be a lower cost design than the traditional full ground source geothermal heat pump system? What I have here is two DOE studies and papers, one from the Federal Energy Management Program and one from the Department of Energy on an assessment of hybrid geothermal heat pump system. And if anybody is interested in that, you see at the bottom of the screen here Andrew and I's emails. So send one of us an email and we can forward those studies to you. And you can read them on your own. Let's pick another question here. Would you expect the evaporation rate to be similar between an open tower and a fluid cooler? Yes, we would expect the evaporation, whether you're doing it directly or indirectly. The evaporation is proportional to the load or the heat input. There may be slight differences due to the airflow rate to the tower, but you're talking in fractions of a percent. The greatest difference that you'd see between the two is that, as I mentioned earlier, that the water treatment is usually easier on a fluid cooler because you only have to protect the materials of construction within the fluid cooler itself, because that open loop water never leaves the tower, with the exception of using a remote sump. So the process fluid is kept inside the coil, so it's inside a clean closed loop. Now, in an open tower, you have to protect all the system components. That ranges from perhaps the galvanized steel on the cooling tower to the black steel pipe to the copper tubes in the chiller barrel. So you're in an open loop system, your water treatment can be much more challenging because you have all these materials that you have to protect. So basically the evaporation rate is the same, but you can run often higher cycles of concentration in the fluid cooler than you can in the open tower, which reduces your bleed required to maintain the water quality. So that's the answer to that one. Okay, another question on the efficiency difference between open and closed loop cooling towers. If you compare the same tonnage open tower versus a closed loop tower, you'll find that the closed loop tower is larger and generally draws greater horsepower than the open tower. But why is that? That's because there are two stages of heat transfer in the closed loop tower. What you need to do is compare this, you're basically comparing apples and oranges. So to get it back to an apples to apples comparison, we need to compare closed loop cooling towers with open tower heat exchanger combinations. That's the fairer comparison, and that's the slide that Andrew addressed, the connected horsepower of the two systems. We concluded was basically the same. You may have a little higher horsepower, fan horsepower, say, on the closed loop tower, but you also then have reduced pump horsepower with the spray pump compared to the cold side process pump. So that the net effect is that they're very similar in total horsepower for the system. How often should you clean heat exchangers? That is really dependent on your specific situation. You should follow, of course, the operation and maintenance manual for plate and frame heat exchangers. But in my own experience, generally that's one of those things that, especially on like condo buildings, that a lot of times that's maintenance that doesn't get done. and that means that the system then pays a penalty. But certainly for a chiller or a plate and frame heat exchanger, it's not a bad idea to clean it at least once a year. But maintaining your water treatment program will help to minimize that. And certainly using a fluid cooler would help eliminate the need to clean the heat exchanger. Okay. Would there be absolutely no scaling in a fluid cooler? No, there would be scaling. As you evaporate water on the surface of the tube, you will leave some of the deposits there, but that can then be controlled by the water treatment program. If your water treatment program is not being done properly, you can actually build up a layer of scale, which then retards your heat transfer and causes you to use more fan horsepower to reject the heat. However, this scaling can then be cleaned off the outside of the tubes because they're easily accessible once you remove the drift eliminators on top of the unit. You can see the coil, you can inspect it, and know that you have a problem right away. You can adjust your water treatment program, or even get in there and clean it with a high-pressure sprayer, if that will help. So. There's a lot of questions regarding the energy use of the two different systems. We only looked at the connected horsepower, which doesn't tell the full story, and that is something that we intend to do in the future, where we actually asked our consulting engineering partners to create energy models for these systems and look at the overall annual energy use between the two alternatives. So that's something we're going to do in the future. But just looking at the connected horsepowers, as Andrew said earlier in the webinar, they're very, very similar. Did the installation cost include the cost of commissioning? No, we did not look at the cost of commissioning in the study, but we tried to capture everything on the design, and that's why we asked IMEG to do the detailed design so we could count up every fitting, every expansion tank, every strainer, every piece of piping and equipment in the system, so we would have a true installed cost. But that's a good point. We did not look at the cost of commissioning in this study. At what low ambient temperature can the cooling tower run effectively without any implementation of winterized techniques? Well, certainly any time you operate a cooling tower in sub-freezing weather, you should follow proper operating procedures. There was an excellent article. It actually was ASHRAE Article of the Year by my good friend Paul Lindahl of SPX Cooling Technologies that reviewed the winter operation characteristics of cooling towers. And the basic conclusion was that following these proper procedures, you shouldn't have any problem at all. And Paul's article, as I say, won ASHRAE Journal Article of the Year several years ago. So if anybody would like that, they can go on the ASHRAE website. And if you can't find it on the website, please send me an email and I'll direct you to it. If the closed circuit cooling tower is not used in winter, will the water be drained? That's a good question. When you're typically, the best freeze protection for a closed circuit cooling tower is the use of glycol. Although in a lot of the mid part of the country where you have relatively mild winters, you can use what's called a positive closure damper hood to retard the heat loss and just basically keep the flow, small flow through the coil to prevent the water from freezing. The standard coil that's used in the industry is a black steel coil that's hot dip galvanized on the outside only. So this type of coil, because it's black steel inside, is not really something that you should drain. If you want to have the capability to drain it, you could upgrade to a stainless coil, and that would solve the problem. Otherwise, in a black steel coil, when you drain it, you're introducing oxygen, which can lead to corrosion. So we would not recommend draining of the coil except in emergency freeze protection cases, say if there's a power failure. The best method is to use glycol, but there are procedures using positive closure damper hoods to minimize heat loss that can be followed, and they've been very successful over the years. Under what circumstances would a plate and frame heat exchanger be used with a chiller to cool the condenser? Generally, what I've found in my experience is there has to be a driver for that. One of the best examples early in my career was a chiller plant on a auto manufacturing factory, and it was located actually next to a cement plant. The cement dust was being drawn into the open cooling towers, and of course that cement dust then wound up in the chiller barrels and basically causing a very hard scale that was very tough to remove. The auto plant decided to take out the open circuit towers and replace those with fluid coolers, and that kept the cement dust out of the chiller barrels. And remember from our discussion earlier, the chiller is operating at 0.6 kW per ton, while the heat rejection is down at 0.06 kW per ton. So protecting the chiller barrel was far more important than letting letting the cement dust get into just the closed circuit open loop, where it could be treated through the bleed and the water treatment system. But there's also other cases where having, just wanting high reliability on the chiller, say for a data center, where you don't want to have, you want to maintain peak performance over time, because that chiller barrel then, the condenser chiller barrel is kept clean. The other instance, it would be where you want to place the heat rejection below the load, which is often done in architectural type buildings for aesthetic reasons.
Maybe we've got time for one more, Frank.
Okay. The typical 0.6 kW per ton, is that based on chiller performance only or a combination of chiller, pumps, and cooling tower? The 0.6 kW per ton value that I mentioned is only for the chiller itself. The system operates more up in the range of 0.72, 0.75 when you include the pumps and cooling tower, which is still less than the 1.1, 1.2 kW per ton that you have with an air-cooled chiller.
Okay. Well, thank you very much, Frank, for answering as many questions as you did. I think now maybe we should hand it back to Jay Ashray to just wrap up for us.
Thank you, everyone, for attending. Have a great day.